All right, so this is going to be a sequence of 3 mini lectures on 3 different topics as part of EAPS536 virtual lecture. I recommend you take a break in between each one just to absorb for a moment. They're going to be different, but those are all important topics that I at least want to give you a very basic introduction to, so you know what the term means and you have something to refer to if you hear it or read about it in the literature. So the Rhine scale is the first topic, and there's some reading in Vallis Essentials, chapter 10.6 with this. The Rhine scale represents a transition between waves and eddies in a turbulent fluid. So what does that mean? So ultimately, it is the intrinsic length scale in the quasi-geostrophic vorticity equation. So this is actually a quite basic equation that we've used in this class. So the time tendency of relative vorticity on the left, plus the advection of relative vorticity by the flow, plus the advection of planetary vorticity is the beta v term. So that's only in the meridional direction, equals 0. So conservation, well, so yeah, so that's it. And so what this really, the Rhine scale deals with is the relative magnitude of the relative vorticity advection and the planetary vorticity advection terms, which are often thought of as the nonlinear term and the linear term in the equations. And so they have characteristic, you can do a scale analysis and say that the u dot grad zeta term has a scaling of u over L squared, and then beta v has a scaling of beta times some u is a velocity. So when are these two terms comparable in magnitude? Is you just set the u over L squared equals beta u equal to each other and solve for L, and you'll get what we call the Rhine scale, which I'll denote as L beta, which is equal to the square root of u over beta. And so u here, I think, is easiest to think about as a characteristic meridional flow velocity in that beta v term, the third term on the left-hand side there. So, but it's not simply defined necessarily. So just think of it as a characteristic flow scale. So what does this mean? So I said it represents a crossover between waves and eddies. So what it means is that if you're smaller than this Rhine scale, what it says is the relative vorticity term is dominant. It's much larger, so you can go back and check the scale analysis and see that is much larger than if you're significantly smaller than the Rhine scale, then this is really vortex advection by itself. So the nonlinear advection by the eddy itself is dominant. So you're in a vortex dominant regime. And you can actually think of this in terms of time scales, which is that the time it takes to go around your eddy circulation once is much, much smaller than the time it takes to produce a Rossby wave. And that latter one is not straightforward to think about what that means, but that's essentially what it means. And so in a really simple sense, it means you don't feel beta. You're rotating fast enough that you essentially, it's as if you go around in a circle before you even notice that F is varying across the diameter of your circle in the meridional direction. So you're just happy as a vortex. Whereas if you are much larger than the Rhine scale, you're in a wave-dominant regime, which is to say that this linear beta term is much larger than the nonlinear advection term. And so what that says is in time scales is that it takes you a lot longer to make one circuit around your circulation than the time it takes to produce a Rossby wave. And so you feel beta very strongly. So you're in the linear regime here, and so you're going to radiate Rossby waves essentially, or at least you're going to generate a Rossby wave. So that's the basic idea. So on a spherical rotating planet, the Rhine scale increases moving poleward. So I just put on here for reference, and I have not purposefully not put actual length scales on the y-axis. But so in this class, you've plotted the Rossby deformation radius as a function of latitude, which decreases as you go to higher values of f. And so what's interesting is the Rhine scale is the opposite direction of variation. It increases as you move poleward. And so again, this is just you have to decide what your characteristic velocity scale is here. So I haven't put the actual magnitude on here, but you can think of these as scalings. And so it's just for reference. So why does the Rhine scale matter? I'm going to give you three different examples. The first is the top level is one that's kind of a practical way to think about it, is the Rhine scale limits the size of extratropical cyclones, or baroclinic eddies, if you will. So this is actually a fairly complicated figure from Vallis in chapter 10, which is on turbulence, but I'm just going to kind of give you a sense of this idea here. Is that so the top row is a distribution of vorticity in a two-dimensional fluid, and then the bottom is stream function associated with that vorticity. And so the left column is your initial state, where there's kind of random small vortices that are distributed throughout the fluid. And then over time, you move from left to right, time progresses forward. And what happens is turbulence in this fluid actually transfers energy towards larger scales, which is to say that you notice there are fewer larger vortices later on. So this is actually just a very, very simple 2D fluid that's being stirred. So you start with lots of small scale vortices, you end up with fewer larger vortices. And so this is a statement in turbulence terminology that energy in turbulent quasi-geostrophic flows tends to grow upscale, which means from small fluctuations to larger organized circulations. And this is referred to as an inverse energy cascade. This is a term you might hear at some point, and they use this term inverse because energy in regular 3D turbulence tends to move towards smaller scales. If you have a large vortex, it tends to break down into smaller vortices and smaller thereafter. And so this is the opposite direction of that, this what we call cascade of energy. It's going going upscale. However, energy cannot go to length scales larger than the Rhine scale. And this is actually because for the same physics that I just described, is that if you get larger than the Rhine scale, or appreciably larger, you're going to generate Rossby waves that are going to move away, and they're dispersive. And so this applies to something like an extratropical cyclone, so baroclinic eddies in general. We formally say that the Rhine scale halts the inverse energy cascade, if that has any meaning to you. So second application is that the Rhine scale defines the spacing between jet streams generally on rotating planets. So here is our Earth. So if you recall, we've mentioned that we generally have one jet stream, but we actually formally have a mid-latitude and a subtropical jet stream, though they're just often merged together. And so, so this is a map showing the potential vorticity as a function of, or the distribution of it. You can see it varies mostly in latitude from low values to high values in the southern to northern hemisphere. And the green arrow just denotes, generally where the jet stream is. And so if you try to just imagine a zonal mean from this plot, what you end up with is something that's that looks like this staircase, these steps. So it looks like a step where there's a step at the jet itself, where there's a very strong meridional PV gradient across the zonal jet stream, and then with much weaker PV gradients in between. And so what's interesting is that eddies mix the fluid, and they actually tend to homogenize PV meridionally across their circulation, whose size is limited by the Rhine scale. So this creates these step-like features, and so you should really think of this in one hemisphere or the other. I wouldn't combine the hemispheres here. But in the extratropics, the distance of homogenization is set by the Rhine scale, or at least limited by the Rhine scale. And so you end up with this in a simulation. This is, again, a fairly complicated simulation, but you end up with something where you get a staircase in potential vorticity. So you have multiple steps, and then at each of those steps is a jet stream. So if you have enough space on a planet, you can get multiple sharp jets. And this sharpness is something we haven't talked about in this class at all, but you tend to get sharp jets, and you'll end up with a PV staircase. You can think of our atmosphere on Earth as having kind of one step in each hemisphere, if you will. Lastly, the Rhine scale likely limits the size of tropical cyclones. I already talked about extratropical cyclones. I'll keep this very brief. Is just the Rhine scale is smallest in the tropics. Exactly what its magnitude is, it depends on a lot of things, but it's generally smallest in the tropics, and so because beta is largest there. And so similar to any other eddy circulation, if a tropical cyclone is too large relative to the Rhine scale, it should radiate Rossby waves away. So, and just note this is relatively new work, actually some work that I did with a colleague that we published last year. And I'll note that you can also talk to a colleague, a student in our class, Kwan Yu, who's working on this problem for his thesis as well. So, all right, that's the end of that mini topic. Okay, the next mini topic we're going to talk about here is something called Sverdrup balance. So it's a totally different topic from what we just talked about. And so there's optional reading here is about ocean gyres. So Sverdrup balance is something that's most generally discussed in the ocean literature, but it's actually something that's important in the atmosphere. And I'm going to talk about it in one specific context. And so that context is the oceanic subtropical highs, which you may have heard about, may not have learned a ton about. So they're generally found in the descending branch of the Hadley circulation. So this map is showing for the January in the north, in the top plot, in July in the south, in the bottom plot is the contours are 1,000 hectopascal geopotential height. And also the colors, and then the vectors are just the 1,000 hectopascal wind vectors you're seeing near the surface. And also just superimpose all these reds are, the H's are the centers of these subtropical highs. And they move around, they have interesting seasonal cycles, and there's a couple of papers included that you can look at for more information I'll mention later on that. So, but the key thing I want to highlight is these subtropical highs, these kind of persistent circulations, have both poleward and equatorward flows as part of their circulations. And so a key, so why is that interesting is that, so oftentimes you may have heard the statement that the geostrophic wind is non-divergent. And so it's actually not non-divergent if F is varying. So specifically in the north-south direction, F varies. So can we show this and what that means? So we can start from the zonal momentum equations, and the meridional momentum equations, du dt and dv dt, which we'll just put the Coriolis term and the pressure gradient terms on the right-hand sides there. So we'll assume steady state, so like we usually do for geostrophic balance. So drop the time tendency terms on the left-hand side of each of these equations. We're going to cross-differentiate these equations. So the y derivative of the first equation there, and you'll notice that what's important here is you're getting a term. You have f dv dy, but you also have df dy times v, which if you think about is beta, so we'll show that in a second, minus d squared phi dx dy. And so if you take ddx to the second equation, you'll get minus f du dx, and then minus d squared phi dy dx. And if you subtract the two, those second derivatives are the same thing. So you can they disappear, they cancel out. And you add them with this equation here. So 0 equals f times du dx plus dv dy plus df dy v. Okay, so what does this mean? So let's first just take a step back and say, well, let's go back to saying, what if f was constant? So then f is not varying in the y direction, so you think of it as an f plane. Then df dy is 0, and so you'll end up with 0 equals f naught times, now this is properly our geostrophic wind, dug dx plus dvg dy equals, 0 equals that. And so that means that the divergence, what's in the parentheses, is the divergence of the geostrophic wind is indeed 0. So the geostrophic wind is non-divergent if f is constant. So just to note, to go back to that. But here we're going to keep f varying, and specifically it varies with y, and that's beta. So df dy is equal to beta. And so, and so you'll notice we can rearrange, we can rearrange this equation, and you'll get beta v equals f times now the convergence of the horizontal wind. So what does that say is that poleward flow is associated with horizontal convergence. So that's interesting. So if you have poleward flow, you expect horizontal convergence there. So we can go one step further and link this to vertical velocity through the continuity equation. So du dx plus dv dy plus d omega dp, which you can think of as analogous to dw dz. So this is omega is the pressure vertical velocity. So upward motion is associated with pressure decreasing with time. So it's positive downwards, but then d omega dp pressure is also decreasing going downwards. So it's a continuity equation. So if you plug that in, you can replace the convergence term with d omega dp, and you get beta v equals f d omega dp. So this equation is Sverdrup balance. So now let's think a little bit more. This may still seem like, okay, what does this mean? And why is this important here? So physically, this can be thought of simply as column stretching because polar flow induces horizontal fluid convergence. So if you have horizontal fluid convergence, you have to stretch the column in some way. So that fluid has to go somewhere. It means that air is going to be moved up or down. And so now we can think more specifically at low levels. So let's think analogously of replacing, just for simplicity, replace d omega dp with dw dz. And then w equals 0 at the surface. So the dw dz is the change of w over some vertical distance dz. But if w is 0 at the surface, then we could just think of dw dz as just w at some altitude. So what that says is if you have equatorward flow, and I should clarify this is for low level equatorward flow, that means you're going to have descent. So you're going to have divergence, and you're going to have air sucked downwards. You're going to force descent. And if you have poleward flow, then you expect there's horizontal convergence, and so air has to move upwards then. So you're going to have ascent. So there's an asymmetry here in the vertical velocities associated with poleward versus equatorward flow, low-level flow. Okay, and so let's go back now to our subtropical highs. So these are maps I showed before, and so I've highlighted in different colors. We'll focus on the North Atlantic subtropical high, where the arrows are now green and brown. Just for as an example. So what this Sverdrup balance effect is that you're getting an enhancement of convection on the western side of the subtropical high, where you have poleward flow, and you're going to have weakening of convection on the eastern side of the subtropical high, where you have equatorward flow. So there's an asymmetry here in convection associated with these, or vertical motion associated with these subtropical highs. And so what's really interesting is that this this actually amplifies a similar asymmetry created by sea surface temperature differences associated with wind-driven surface ocean currents. So this map here just shows the colors denote mean sea surface temperature. I believe this is annual mean. And so you'll notice if you look in the ocean basins, you usually have warmer water on the western side of an ocean basin. And so ocean currents are generally bringing warmer water poleward on the west side and cooler water equatorward on the east side. And so what that means is we expect generally, especially in the tropics and subtropics, that air will tend to rise where the sea surface temperatures are relatively warm, which we learned about in an earlier lecture. So this actually is a very similar, it amplifies the same asymmetry, and is really kind of generally important for thinking about subtropical highs in general. And so I just have at the bottom right there, if you want more information, there's a little bit of reading in Hartman about the ocean circulation. And then there's 2 papers listed that I'll also post on Blackboard, Rodwell and Hoskins in 2002 and Seegerdal 2003 on this subject for more information. All right, and now we have our third and final mini topic, very unrelated to the other 2 topics, but another concept that I just really want to introduce, which is called the gross moist stability, or GMS. And this is a very messy topic in tropical meteorology, so I'm going to give you just a little taste of this. And so there's a paper that I think is the most, to me, the most useful starting point is Inouye and Back in 2015 in Jazz. Okay, so the gross moist stability, GMS, what is this? This is a really bizarre sounding term. It has the word moist in it, so it's specific to moist circulations. And so formally, you can think of it in the most basic terms as the net export of moist static energy from a convecting region by an overturning circulation. There's a lot there. Let's unpack that in words and then in schematics. So the basic idea is that typically large-scale overturning circulations remove moist static energy from their convecting region. We'll talk about why that is in a moment, but the ascending branch of such circulations typically occurs where MSE is relatively high. So we said convection is usually found over relatively warm water, where the moist static energy is relatively high. So those two together mean that this process, the overturning circulation, acts to weaken, or this removal of moist static energy acts to weaken the circulation itself. The overturning circulation is in some sense always fighting against itself, if number one is true. And hence it's phrased as a stability. It's a sort of an energetic stabilization against the development or maintenance of an overturning circulation. This is an important but a very messy topic or concept in tropical meteorology. So we're going to try to unpack it a little. All right, so let's see if we can understand this conceptually and quantitatively a little bit more. So let's go back to the equation for moist static energy. Just as a reminder, we'll denote it as H, which is again the sum of potential energy, sensible heat, and latent heat. So we had learned before that the typical profile in the tropics of moist static energy looks something like this, where it's a maximum at low levels, then it decreases to some minimum, and then it increases again in the mid-troposphere, and then it increases again up near a higher value near the tropopause. So recall that this mid-tropospheric moist static energy deficit exists primarily because air is relatively dry there. So temperature can't vary much horizontally in the tropics. So it's moisture, it's specifically drier subsaturation in the middle free troposphere. Okay, so let's understand, let's think about what can change the moist static energy in a column. So we're going to walk through this again. I'll put up the schematic and then we're going to step through this here. So we're going to think about the column integrated moist static energy. So denoted with the angle bars H here. So it's the vertical integral. And so we had learned before a budget equation for the column integrated MSE. And so I'm going to write a slightly simpler version than the one we had before. So on the left-hand side is the time tendency of the column integrated MSE. On the right-hand side, we have these three different terms here. We have the surface enthalpy fluxes, so latent and sensible heat. That's F naught, so that's the fat arrow in the schematic on the left coming in from the surface. We have net radiative heating, so there's radiative flux from the surface into the atmosphere at the bottom, and then there can be a radiative flux from the atmosphere out to outer space through the top. And so the difference between those two is the net radiative heat, net heating or cooling of the atmospheric column, so changes in temperature, so sensible heat due to radiation. And then the third term here is, which we didn't spend a lot of time talking about before, is the circulation term, the advection term. And so I'd already superimposed on here a gray overturning circulation in assuming that this is kind of a convecting column here. And the idea is that overturning circulation can have a net transport, a net advection or convergence or divergence of moist static energy into the column. And so why is that? We have to think a little bit about that. You might think at first, shouldn't that just be zero? Okay, so the question then is, will this overturning import or export moist static energy into the column? Which is not actually a straightforward question because of how moist static energy varies with altitude, the answer actually depends on where within the column the inflow and outflow occurs. And we're going to show that explicitly in a moment. Think about a couple of cases. And so importantly for mass continuity, the vertical distribution of inflow, which is to say inflow means convergence, and outflow, which means divergence, is directly tied to changes in vertical velocity with altitude. So the continuity equation is shown there, and just conceptually, it just means if you have convergence of air horizontally, that air has to go somewhere. It's going to go up or down. And if you have divergence of air in a layer, that you're going to have air sucked up or down within the column. Okay, so often then how this is thought about is in terms of the vertical profile of vertical velocity. So I'm showing you two schematics, and this is from Inouye and back in 2015. different vertical profiles of vertical velocity. And so it's noted on the x-axis, it's minus omega, which is it's just to say you can think of as analogous to vertical, regular upward vertical velocity being positive. And and so there's two different cases here that we're going to go through. So the first one on the left is one we call a bottom heavy profile. You can see that the vertical velocities are weighted towards lower levels. And this is one, if you look at d omega dp is positive, so vertical velocity is increasing, moving upwards over a relatively short layer or thin layer near the surface. So at low levels. And so that implies that there must be inflow into this column there, and that happens since it's confined into the surface. This is where you're bringing in MSE rich air, so high moist static energy air. And then meanwhile, there's a relatively deeper layer in the free troposphere, or at least the upper and middle free troposphere, where vertical velocity is decreasing more gradually. And so outflow is spread out over a broader layer that includes lower moist static energy air. So the net is that, so you have high moist static energy air coming in, lower moist static energy going out, and the net is a net import of moist static energy into the column. And so that implies a negative gross moist stability. And so it's unstable. We call this unstable. And we say unstable because then again, it's essentially enhancing the radial or the gradient in moist static energy between the convecting region and its environment. So meanwhile, on the right is what we call a top-heavy profile, where vertical velocity peaks higher up in the troposphere. And so the reverse is true now. So now we have lower or inflow over a broader layer that includes lower moist static energy air above the boundary layer in the lower free troposphere. And then the outflow is confined to the top of the troposphere where the moist static energy is higher. And so the net result is a net moist static energy export, which is a positive gross moist stability, which is just to say it's stable. So the overturning circulation is being stabilized by this effect, essentially, because the moist static energy difference is being reduced. So these are two nice cases. So what's interesting is the top-heavy profile is typical of convecting regions and convecting systems in the tropics, i.e. a positive gross moist stability. The stable case. But what's interesting is that moisture, radiation, and dynamical feedbacks can act to shift the vertical velocity profile towards a bottom-heavy profile. But how this happens is really not well understood at all. But this is really important, this idea of this transition, because one hypothesis for how a region of disorganized convection transitions to develop an organized overturning circulation is that the region must have a transient period with negative gross moist stability. And so, yeah, so the physics of this are not well understood. And so just as a couple of examples of potential places where this may apply is the Madden-Julian oscillation, as well as tropical cyclogenesis. So we'll talk about tropical cyclones next week, though we probably won't talk about GMS in this case. Lastly, I just want to give you, now I haven't actually given you an equation for what this gross moist stability is. And so this is the formal definition, I'll say a formal definition of GMS. I think it's the most relevant. There's several different definitions though, and it's given by here. Gamma is defined as the net export or divergence of moist static energy, so del dot HV, so column, I should say column integrated. So you have the net export out of a column, divided by, so that the numerator is basically what we've been talking about this whole time, and so the sign is determined by that numerator, but the actual quantity is defined as divided by the net export or divergence of dry static energy, which is just the sensible heat plus the potential energy. So what the heck is this net export of dry static energy? This is essentially a measure of the intensity of the convection itself in general. So a convecting region always exports dry static energy, since a dry air parcel can't rise unless it has higher dry static energy, i.e. it's warmer than its environment. This is a really unique thing of a distinction between dry and moist air. So in this sense, then this dry static energy export always occurs with overturning circulations. So it's a way to measure the intensity of the overturning circulation associated with the convecting region in general. So I'm going to leave you here just with a definition from Inouye and Back 2015 is that how they define it is the GMS represents the efficiency of export of some intensive quantity conserved in moist adiabatic processes. That whole term, in our case, we're just talking about moist static energy per unit intensity of the convection. So, and if you're curious to know what that could mean, or how they think about it, I encourage you to go to this paper. They look at this and also apply this to observations, which I think is why I like this as a starting point paper for people to get to know about this topic more. So with that, go ahead to Blackboard, answer a few questions about these mini topics. Thank you.